So let's go ahead and look at a second memory dump. This is a Stop9E, or a user mode health monitor bug check. So once again, we'll go ahead and fire up the debugger in administrative mode, and we'll go ahead and open up the crash dump. Here we are. In fact, we're going to look at 3 crash dumps very quickly. They're all from the same system. They're just collected at different times after different configuration changes. So let's go ahead and see how these turn out. So I'm bringing the first memory dump into the debugger, and we'll go ahead and scroll back and take a look at what we find. We can see that this is a Windows 7 kernel, build 7601, which is 2008 R2 Service Pack 1. So we'll scroll forward and see that we did in fact get a 9E stop code, and debugger thinks that it was RHS.exe that caused the problem. So we'll just start out with the bang analyze-show command. And as we can see, it is a user mode health monitor bug check. Essentially, things didn't happen in a timely fashion. This process was the one that failed to satisfy the health check, and here's the timeout that occurred. So we can do a quick check there with the question mark 4 Baker 0 divided by 60 seconds equals 20 minutes. So we know that the RHS process, most likely that's what this process is, we'll take a look at it, failed to respond to the timeout within 20 minutes. So we're just going to take a look at that process with the bang process command. Now a lot of information goes scrolling by, so we'll just wait just a moment and we'll go ahead and get back to the beginning. All right, there we go. So we're just going to page up right to the top. Yes, a lot of different threads came out of this process. So here we are right at the top. So we issued the bang process command, and as we could see, it is indeed the RHS, that's the resource hosting subsystem for the cluster service. And if we start looking at the different threads, you can see that here we've got one that's been exactly 25 minutes. And this is important because we know that the deadlock timeout period is 5 minutes, and we know that the RHS is allowed to spend up to 20 minutes, so we have a total of 25 minutes that the system has essentially been hanging. So if we were to look at the stack of that particular thread, we can see it's doing some sort of common create with NTFS. So NTFS is then doing some sort of deleting of an SCB, and then it tries to acquire a guarded mutex, which is a lock. So this thread is waiting on a lock. Now if we were to scroll down and look at some of the others, this one's been waiting almost 25 minutes. It's also waiting for a guarded mutex or a lock. Same thing here, we've got another thread, almost 25 minutes, and once again, it's waiting for a guarded lock. Here's another thread that's been waiting exactly 25 minutes, and it's waiting for a guarded mutex. So this appears to be a locking problem at this particular point, so we can issue the bang locks command. Now, a lot of information is going scrolling by. In fact, this command would take lots of time to execute because, let's face it, there's a lot of locks out there that have been accumulating over 25 minutes since this system has been hanging. We could take a look at one of those locks, and in fact, the kind of locks that you want to focus in on are those that are exclusively owned. Here we have an exclusively owned lock on the SRVNet service share lock. So the thread with the asterisk next to it, you can see the asterisk there, that's the thread that owns the lock. And these threads are all waiting on the lock. So we can, in fact, take a look at that thread to see why it might be waiting. So we'll do a bang thread on that. And if we look at its stack, yes, there's the SRVNet driver. It's doing some sort of deleting of a share. And there it waits because it undoubtedly is waiting for a lock too. So As it turns out, there's probably thousands of these deadlocks that have evolved over the last 25 minutes. So let's go ahead and take a look elsewhere. I'm going to issue the bang running -it command to see what was out there running on the different CPUs. So you can see we've got 24 CPUs. So as we page up to the beginning, here we go. There's where I issued the command bang running -it. We can see CPU 0 was idle. So was CPU 1. CPU 2 was doing some sort of MPIO, some sort of storage access. CPU 3 was idle. CPU 4 was also doing some sort of storage MPIO and MSDSM type access. CPU 5 was idle. And here CPU 6 is actually doing some work in the Emulex driver, the elxfc.sys. So we'll go ahead and scroll down, see what else we see. Idle, idle. All these CPUs are idle. That one's idle. That one was the actual CPU that bug checked when the NetFT Watchdog timer expired. So as we continue to scroll down or page down, you can see that they are in fact all idle. In fact, if we did that bang running command by itself to show me non-idle threads that are running, there's only 3 threads out there that are running. So it doesn't appear that we've saturated our CPUs by any means. So it doesn't appear to be a CPU issue. But we can check a little more and do a bang ready. And look at this. There are no ready threads and only 3 running threads. So we don't have a CPU problem. Let's go ahead and check physical memory. I'm going to do the bang VM command. This will take just a moment and it'll figure out how much page file space, how much free RAM there is, and it'll show us all the memory usage by the different processes out there. So let's go ahead and scroll back up. Here we are. I issued the command right here, bang VM, and we can see the page file utilization. Now, this time the current value, the minimum, and the maximum are all the same. They're set at 16 gig. And if we look at the free space, we can see that's a little less than 3 gig. So when you compare the 3 gig to 16 gig, you can see that we're very low on page file space. We've got less than 25% free. The problem is that even though we have room, the page file gets internally fragmented. That's why we always want to have at least 50% of that page file free on a busy system. Here, we don't even have 25% of it free. And if we look at physical memory, out of 32 gig, we only have 50 megabytes free. That's incredibly low. So not only have we run out of page file space, we have very little free memory as well. Now, if we scroll down and see what might be consuming all that page file space, you can see here that there's a process called perfmon, and it's literally using almost 5 gig by itself. That perfmon process happened to be collecting the thread object, so it was very memory intensive. You never want to collect the thread object with perfmon. We'll talk about perfmon quite a bit in the next module. You can see there's other processes such as this antivirus, and they're all using their fair share of memory. In fact, when you look at all that memory, the total private usage is about 10 gig. And remember, we've only got 16 gig on this system, so the system overhead is certainly explaining where the other memory went. So this system has literally run out of memory, and there's very little page file space available. So that's why this system essentially hung, causing the stop9e bug check to occur. So let's go ahead and look at the second memory dump. Okay, so I'm going to exit out of here, bring up a new incarnation of the debugger, and we'll just open up the second memory dump right there. So, same version of the operating system. A few months later, we've got an exact same crash going on. Once again, The debugger says that it's probably caused by the RHS process. If we do the bang analyze -show command, you could see that it is indeed the same for Baker 0 timeout that has been expired. So let's go straight and look at memory this time. So I'm going to do a bang VM command. And we'll just scroll back and take a look at the output here. Here's where I issued the bang VM command, and you could see the page file is still set to 16 gig. And we still have very little page file space available. But look at the physical memory now. The physical memory has been bumped up from 32 gig to 64 gig, and we've got about 14 gig of free pages. That's great. We're not running on memory fumes. But what is taking up all of that page file space? That's the next question we need to answer. Well, if we scroll down just a little bit, you'll start seeing the paged pool usage. And you can see here that the page pool usage is approximately 36 gigabytes, which is huge. That is what is taking up most of the page file space. So even though we have free memory available, our system is grossly using paged pool for some reason. So we want to take a look at what's consuming all that paged pool memory. So I'm going to do the bang pool used command, looking at paged pool, and I just want to see the top 5 consumers. So the command goes off, and here we can see the tag here is the MMST. That's the tag for the memory management section objects. And as you can see, it is utilizing essentially 14 gig of memory designated to this paged pool structure. There's several other paged pool structures such as NTFF. And as you can see, if we scroll all the way to the far right, you could see what those data structures are. So there's the section object. Then the next is some file control blocks, name cache data, I/O symbolic links, and parsing names. So of the top 5 consumers, we've got a 35 gig total being allocated to paged pool. And that is what's chewing up all the page file space. So let's go ahead and take a look at one more crash dump. I'll bring up another incarnation of the debugger. Open up the crash dump. Let's look at memory dump 3. So once again, it's the same system, same crash, same timeout value. So let's go straight to the memory and see what's happened now. So I'm going to do a bang VM and let it tally up the various memory pools, and we'll take a look at that. So as I scroll back up to the start, here we can see that we've got not only one page file, we now have a second page file. The first page file of 16 gig is totally used up once again. It has nothing left. This 32 gig page file has very little space too. So once again, we've filled up our page files completely, and we only have 379 meg of memory. So we've run out of free memory, we've run out of page file space. Let's take a look at that pool. Oh, now we've got 75 gig of paged pool data structures, and we've even had pool allocation failures. The debugger's very good at pointing out anytime we failed to allocate pool. So we can certainly issue that bang pool used command again to determine exactly what is chewing up all our memory pool. As we can see, it is those same data structures, the MMST, the NTFF, FMFN, IOSI, and IONM. And they're accumulating over 75 gig worth of paged pool. And as a result, it's totally filling up the page file, and we're running out of memory. So, to make a long story short, there are known issues in Windows Server 2008 R2, specifically with this MMST type of paged pool allocations. They're utilized primarily with backup type operations when we're backing up files. And Microsoft has addressed the algorithm in Windows Server 2012 so that it doesn't use quite so much of these MMST pool allocations, and the system will be much more stable. So it didn't matter how much memory we continued to add to this system, because if you look at the amount of memory we've now got on the system, is 96 gigabytes of memory, yet we still utilize that much. So the advice here is to, research that MMST pool tag on the internet and see if there are any known issues, which in this case there were. And the recommendation is to upgrade to Windows Server 2012 or later. So hopefully this gives you a pretty good idea of viewing the various CPU or memory or page file related resources to see which ones have in fact been depleted.